So what we're looking at here is Intergalactic, chapter 16, actually. It's chapter 16, Intergalactic. So we'll fix that. Question number 9, and this is the Spigspam question. We have 3 particles held in a stationary line. The charges are A, B, and C, and they are negative 30 microcoulombs. So I'll do my negatives in blue. So that's negative 30. B charge is 20, so positives I like to make red. It's microcoulomb. And then over here is negative 90 microcoulombs. So it's going to be blue in a second. But A and B are separated by 2 Spigspams, which is some made-up unit of the Intergalactic. And charge C is actually about this far away. Maybe that's exaggerated, but it's negative 90 microcoulombs, because this distance here, this separation, is 4 Spigspams. So the question is, rank the charges from greatest to least by the amount of force acting on them. So when we look at a problem like this, first we are ranking. So while we might want to immediately pull out Coulomb's law, which is F equals KQ over R squared, we don't actually have to do that, especially in this case here. Let's do this. Let's think about this for a second. If we were looking at this, let's start with charge A for a second, right? Charge A is being attracted to the 20, and it is being repelled by C. So that's the force due to, that's the force due to B. And this is the force due to C, okay? If we look at this here, we are being pulled from the A, and we are being pulled from the C. And if we look at the last one, we are being pulled here from the B, and then we're being repelled from the A, right? So if we just wanted to, hold on, did I do this correctly? Charges A, B, and C, negative 30, 20, negative 90. Charges A and B are 2 Spigspans. B and C are 4 Spigspans. Rank the charges from greatest to least. Okay, so we know that all of these are going to subtract from one another. Okay, so we actually didn't get lucky in this problem, and we can just say like one adds together, so it'll be greater. We are actually stuck going back into Coulomb's law here. So what we need to do is we only actually need to get 3 Coulomb's law equations here, because these forces right here are the same. They're equal and opposite. These forces right here are the same. They're equal and opposite. And then actually, and this one's a little weird, these forces right here are the same. They're equal and opposite. So let's just get those 3 forces, and then we can add and subtract them at will. So let's do the force on charge A from B, which is equal to the force on B from charge A. And it's going to be KQQ over R squared. Since all of these are going to have K's in it, I'm going to ignore the K's because they're all going to upscale by the same factor. And since they're all in microcoulombs, I'm actually going to ignore that too. And because they're all in tens, 30, 20, 90, I'm going to ignore the tens digit. I'm going to pretend they're just 3, 2, and 9. It's kind of like a cheater's way out, but it's a faster way to do this problem. So getting rid of the K, for the first one, we're going to get 3 times 2 divided by the Spigspam, 2 squared, which gives me, what is that, 6 over 4. For the force on charge A from C, which is the force on C from A, those are equal. This is going to be 3 and 9 divided by, we got to be careful here because that's 2 plus 4, so that's going to be 6 Spigspam squared. 3 and 9 is 27, right? So that's going to be 27 over 36, which is some number, right? And then last but not least, we have the BA set up. So the force of B and C, which is equal to the force C to B. And that's going to be K, which we've admitted. That's going to be 2 times 9 divided by 4 squared, which gives us 18 over 16. Okay? These aren't nice denominators here to make anything useful. I guess if we wanted to, we could at least make this one semi-useful and call it 24 over 16 to at least compare the AB to BC's. But at this point, you are just saying, look, I know what each of these numbers are. I know this number right here in between these two is 6/4. I know the number between the B's and C's are 18 over 16s. And I know the numbers kind of at the edges here are 27 over 36. So all we need to do now is we need to make a decision. Which direction do we want to call positive? Which direction do we want to call negative? Traditionally in your science classes and math courses, we call right positive and left negative. So if we wanted to kind of go through this and we'll kind of go this A to C. If we start with the A charge on the far left, we're going to have 6/4. It's positive because it's going to the right, minus 27 over 36. That's some number, right? We will get a number out of that. If we do this for the B charge, we've got 18 over 6 acting to the right, 6 over 4 acting to the left because it's actually right here now. So that's negative. So we're going to have 18/16 minus 6/4. This actually gives us some negative number here, which implies that this force here, this net force, is acting to the left, whereas the positive we had in the first answer implied it was acting to the right. And in the last one here, we have the positive 27/36, which is a silly number, minus the 18/16, and in this case here, we're going to have another negative number. And at that point, we just rank them 1, 2, 3. Biggest to smallest, however we want to do that. Okay? And that's it. That's the problem. We just kind of had to do 3 Coulomb's laws. We made life a little bit easier by getting rid of the K's because they all had this constant out in front. So who cares? They all factored up by the same amount. And we also got rid of all the zeros floating there because that would just add extra zeros to the end of these, right? So we got rid of them. We kind of ignored some units there to do that because we were just ranking. If we wanted exact values, we would have had to put that in, but on a ranking system like this, just take your even numbers you got or take your solid numbers and go with it, okay? So with that, number 9 is finished. No Spigspams for you. Come back 1 year. Adios.